Good morning, everyone, and welcome to the talk. Today, my topic is Spark and Plus HBase, bringing HBase data efficiency into Spark with data frame support. My name is Zhang, software engineer in Hortonworks. Currently in the Spark team, mainly work on Spark and Hadoop. Specifically for Spark, I help to bring on the first two GA official Spark release from HTTP 2.2 and 2.3. I'm actively contributed to the Apache Spark Young HBase and Berry. In Spark, I write some org support, high version upgrade of heap API. Then HBase part, I mainly work on this Spark and HBase connector. My experience is focused on computer networks, distributed system, and machine learning platform. I used to work in Cisco, Juniper, Samsung research lab in North America. Okay, that's about myself. Now let's go into our topic, why we revamp the existing HBase connector. Actually, we have some big customers. They use HBase heavily. Also, they begin to use Spark. They want to access the HBase in Spark. At that time, we need to evaluate the solution. We have two choices. The first one is RDD through the HBase, through the standard HBase Hadoop input format. The second choice is data frame. But that is, I think, Spark 1.4 data frame is a new concept, but all of us can see it's the trend. In 1.6, then we have the data set. In 1.2, I think in the incoming Spark 2.0, the data set will be unified with the data frame. So in the long term, we decided we take the data frame approach. Next step, we look around to see whether there is already open source solution available. There do have some, but they are not good enough. So mainly in the Spark HBase upstream, the main support is the RDD level. I believe many people joined the talk yesterday, presented by Cladera for Ted and Jensen. The work they are mainly doing is the RDD support, for example, the scan and the bulk get, and integrate with Spark streaming. In the current upstream implementation, actually, if you run some query, you will see some data loss or data duplication. Data loss means in your query, some record is supposed to be there, but it's not returned to your query. Duplication, some records may appear multiple times. This is a very critical issue and not acceptable to any customer solution. There's some other solution, but it's very advanced usage of the Spark. They use a coprocessor, ship the lineage, even ship the RDD lineage to the coprocessor. All those, they can push down the aggregation, very complicated those algebra. But to make this work, they have to put their own customized optimizer. In the catalyst, they write their own catalyst that's optimizer. For example, they rewrite the aggregation, all those stuff, then push construct those aggregation to the RDD, then push the RDD to the HBase coprocessor to perform the task. It's a very advanced use case, but it's very complex. HBase is a critical service deployed in any enterprise. If we take that approach, it's a high risk. Also, because it's very complicated, use a lot of hack, it's very hard to maintain the code base. Everyone, if you are familiar with the Spark community, you know every release the Spark evolve very, very fast. From 1.4 data frame, external data source, 1.6 they have the experimental data set, 2.0 they unify the data frame and the data set. all those stuff, the internal API is changed dramatically. It's very hard to maintain. Then we decided we need to write our own connector, because I used to write the awk, those file support, so I'm quite familiar with this one. So we decided to take this approach. So what improvement we made? We combined the Spark and the HBase. In the Spark side, we use the Catalyst engine for the query analyzer, query optimization, and the strategy. The Catalyst analyzer is just to resolve your unknown attribute or unknown table or unknown UDF to the, then they optimize your query plan. Optimize query plan, a typical case, for example, you can push down your filter as low level as possible. Then they use a strategy to construct the DAG of the RDD, that's physical plan. We don't touch any place in this side. We don't do our own work in the inside of the Catalyst. We totally leverage the Catalyst. We keep it simple, easy to maintain. For HBase, we mainly use the fast access for the KV store. We implemented the standard external data source with HBase built-in filter. We don't use a coprocessor. Yeah, we may sacrifice some performance. For example, for aggregation, we don't push the aggregation into the region server side, but we keep it simple, also easy to maintain, and maybe less error. Next thing, we do care the performance, because our customer is they deploy really big cluster. The performance is critical to them because they do the online data analysis. The data coming from Spark stream is on flight. Also, the data sitting in the HBase, they need to join the data from the streaming side and the data from the HBase side. All this happen in the data frame level. The streaming, we know, is not natively support the data frame, but streaming essentially is RDD. We can easily convert to the data frame. So for any performance in Hadoop, we always say data locality. That is, move the computation to data. That here, in this context, we move the RDD task to the region server. The second is partition pruning. There are so many region servers in a table, in a HBase cluster, but only part of the region server holds the data requested by the user. We only perform the task on the region server that having the data requested. All the other region server, if they don't have the data, we don't do anything on that region server. Column pruning and the predicate push down. Column pruning, when we get the request from the Catalyst engine, typically is a build scan. Two parameters we have. One is the requested column, the other is filter. The request column, maybe the HBase, maybe you have 100 or 1,000 columns, but we only request 10 columns. So when we construct the scan, we only push those columns into the scan. So on the region server side, they will only return the requested column, no matter how big the HBase table column is. The predicate push down in your query, typically you have where clause. We push those, use the HBase native filter. There's some challenges. This part, I will talk it later. So we actually implement a very standard external data source API. We implement it on top of Spark 1.4. Then we take half day to upgrade to 1.5. Maybe take 2 hours to upgrade to 1.6 or Spark 1.6. It's very easy to maintain because no matter how Spark changes, those external API keep stable. Because we implement this full-fledged data frame support, we can run the Spark SQL and the HBase. Also, we can run the integrated language query, use the data frame directly. There's no difference between this HBase data frame or any other Parquet data frame, JSON, Avro, Awk. They are same in the Spark world. No difference at all. Anything supported by the standard data frame is supported by the HBase data frame. We don't assume any encoder, decoder, or any specific format to the HBase table. Somebody may be familiar with Phoenix. I'm not an expert there, but I think probably Phoenix needs some special encoding, decoding. You need to import your table to the Phoenix. They maintain their own schema, and you can query on Phoenix. But yeah, they are targeted to different applications. I just point out the difference here. Any table, your existing HBase table, as long as it follows the Java primitive type, you don't need to do any change. The next one is composite key support. In HBase use case, a lot of people put the composite key in their key part. It's quite challenging to support the composite key because the column, the partition pruning. Here we can see in the row key, we have two subkeys, key 1 and key 2. That is defined by user. This, yeah, I will talk it later, but here I just bring it up. This is the column name in the Spark table namespace. This is the column family. This is the column qualifier. This is the data type. For any column, we have the column in the HBase, we have the column family. Specifically for row key, this we reserved for row key. This column qualifier is this K1 and K2. These two mapping to the Spark table namespace. This is how we define the composite key. The next, the customer requests some Avro support. It also is a very typical practice a lot of people, they receive the data from Kafka or some other streaming queue, and put those data with, I think, Avro format or some other format to the HBase. We also want to support this kind of application. So we have the native Avro encoder and decoder. And this part of code, typically, we know in the Spark package, the database, they have the Avro package. We pretty much reuse their code. But because that code is not in the Spark upstream, so we have to make the copy, do some minor change to make it work in our case. Hello? Okay, thank you. Sorry about that. So far, any question? Yeah. Here we have an example schema for Avro record. If you learn Avro, this is a typical example for Avro support. We have the 3 columns, the name, favorite number, and the favorite color. We convert this record to the Spark data type directly. So with this Avro support, actually we can support the complex Catalyst data type. Certainly, if we don't use Avro, we actually have the customized cities to support the complex data type in Catalyst to do the serialization and deserialization. But the user have to write their own code. If you leverage the Avro, then you define the Avro schema. You don't need to do that. Okay, we give that's the background. Now, how do we use this connector? The first thing, like any maybe the existing HBase connector. The first thing we define the mapping between the Spark table and the HBase table. This is the first line is for HBase table. Which table we are operated on? We say it's table 1. This is the HBase table name. We have to tell our connector what's the row key. Here I use a single key, not a composite key to make it simple. The next is the mapping between the Spark table's namespace to the HBase table namespace. For this, when you query the table, if you do the print schema, you will, in the Spark, you will see column 0 to column 8. Underline each column mapping to the HBase with the column qualifier, column family, and the column qualifier. The first one is special for the row key. All the other is the standard HBase concept. One thing I want to mention here, I show 9 columns. One of them is row key. But in HBase, maybe you have 100 columns or even more. You only need to define those columns. For example, you have 100 columns. You only need to define this 9 columns. If in your query you only refer to this 9 columns, you can just skip all those other columns. But of course, if you want to define, it doesn't hurt. Yeah. With this catalog defined, it typically is the mapping between the Spark and the HBase. It's just for testing. When we already have a data frame, confirm the format of our mapping, we can easily write to the HBase with the standard Spark external data source API. We prepare our data, but in your case, maybe you already have the data frame. We already defined the catalog. That's the mapping between the HBase and the Spark. Then we pass this as a parameter, then use our data source format to save. Then this will write to the table. Here, this one, new table, if you specify this, means when we write it, if the table does not exist in your HBase, we create one with 5 number of region server. This part a little bit confusing. Maybe we need to reconsider, make the name self-explain. Okay, this is the writing path. Actually, when you, for example, you process the data, after you're processing the data, you can call this query, you call this writing path to write to your HBase. And later on, probably we will work in the community to support more advanced, maybe bulk put. Those currently, this is the basic interface. Okay, after writing the data to HBase, how do we read it and operate on it, run query on top of those HBase? We first define a facility function. This is a standard external data source reading path API. Spark SQL context read passes our parameter. Then using our format, we do load. Then with this facility function, we do the data frame equal to with catalog. Then this data frame will maintain all the information mapping between the Spark and the HBase. If you do the df print schema, you will get all those column 0, column 1, column 2 to column 9. Also, each column have your data type. If you do the df explain, it will maybe, I don't remember exactly, maybe physical IDD or logical IDD. Yeah, now we have the data frame ready to use. This data frame, there's no difference from other Spark standard data frame. You can do whatever API supported by the data frame. Here, let's see, simple example. Data frame filter, we filter on column 0. Also do some filtering on column 4. Column 0 is as we talked previously, is a row key. Row key is very critical. Although the data frame is no difference, but because of the design of HBase, row K is very critical to the performance in your scan or get. A lot of our optimization depends on the row K. For example, the partition pruning. Why I write this, this query doesn't make sense, because I run a test to make sure all the data got retrieved correctly. There's no loss, no duplication. So yeah, when you do show, you will be able to see maybe by default 20 rows in this data frame. Okay. If you are not familiar with the data frame API but familiar with the HBase, you can run your HBase on this data frame. The first step is register temp table. Then you SQL context SQL, then select count from the table. You can do join, aggregation, or any other supported by the SQL semantic. This is just one of the data frame. You can interact with any other data frame. For example, here we can construct another data frame from the org, or from Python, or from JSON, or from Parquet, any data frame. Then you can use our connector to provide another HBase data frame. Then you can do join or aggregation or all those complex SQL query between these two data frames. Yeah, the use case is quite simple, but in practice, I think it's quite typical, because for different solutions, you have different use case. For example, for HBase, typically it's very good at the point lookup. For Hive, for org, maybe your query get high performance when you do some batch scan. So in your enterprise application, maybe you put some data to Hive store, put some data to HBase for your different application. But later on, you want to do some join or query on all of these different data sources. So you can do something like this. The Spark provides you such facility, and they're very easy to integrate the different data format or data source. Yeah, we will have the tech review from HortonWorks, but currently it's under my personal GitHub. We will publish, currently we publish as a Spark package, but under my personal GitHub. We will publish this Spark package using the HortonWorks GitHub account later, but now because of the timing, we have to do this. Because a lot of customers want to use it, we need to do the publish first. If you go to the Spark package, search for SHC, you will find this page. You can do -- package in your Spark shell or Spark submit is a standard use case. And if you want to use this as in your project, you just add the dependency in your POM file. If you are really interested in the source code, this is HortonWorks GitHub. You can, this github.com hortonworks/SHC. You can download it or compile it. It's a POM Maven project, Maven package, and Maven test, those standard stuff. Okay. I already introduced how to use it. It's, if you are familiar with the data frame, it's quite straightforward. If you're not familiar, you can see the Spark really provide a very powerful user API. I think that's the most attractive part of Spark. Next, we introduce the overall architecture. We assume in your cluster, the HBase cluster is deployed along with the Spark cluster side by side. For example, you can deploy the HBase cluster and then deploy the YARN in the same cluster, or deploy HBase on YARN. So the Spark can run along with the HBase. Why we do this? Remember that we need the data locality. If you don't deploy like this, yes, you still can run it. There's no problem, but maybe you hit some performance issue. Here, suppose we already have a query come in. The driver will compile this query, then construct the task, send to the executor. Then each executor will send the scan or bulk get to the region server. I only show 4 region server, but if your HBase cluster, maybe you have 10 region server or even 100 region server. But with only this 4 region server having the data you requested, driver will send a task only to these 4 regions, 4 executor, because in the driver side, it compiles the query. It already knows that all the other region server is not doesn't hold any data requested, so we don't send any task to those region server. So this actually is a partition pruning. The second we want to pay attention is each executor only send the request to its local region server. Yeah, here the executor and the region server are running on the same host. Only send the request to the local region server. That's how the data locality achieved. It doesn't send a request to other part. The third part is for the executor, when it receives one task, it will send multiple scan and multiple get to the region server. For here, the driver actually constructs 4 tasks. 4 tasks in the Spark actually is the 4 partitions in one RDD. Each partition corresponds to 1 task. But all these tasks, one task actually consists of multiple scan and gets. This scan and gets is grouped by the region server. If we don't do like this, we will, for each scan or bulk get, we construct 1 task. Then for this one, we will have 1, 2, 3, 4, 5, 6, 7, 8, 10 tasks. 10 tasks, but we only have 4 region server. That means we have to schedule 6 tasks to other executor, or we have to wait for the first wave of the task get finish to schedule the second wave of the task. Yeah, this is a high-level concept for partition pruning, data locality, then how to organize the task, construct the RDD. The data locality, yeah, I maybe need to mention. Here, the executor only sends the task to this local region server, but how come it can go this way? Because in the driver, we retrieve the metadata from the HBase metadata table. We know in each region server what's the host for this region server. Then when we send the task, actually in the RDD partition, there's a get prefer location. We send the get prefer location to the host address to this region server. So when the scheduler schedules the task, it requests the prefer location. It will try its best to assign the task to this specific host. There's some tricky part, how to do all those partition pruning stuff. This is some background knowledge. In the integer world, we always have 0, 1, 2, 3, 4, 6 larger than the negative number. If we say x larger than 0, we can start from here, go all the way to the right. But the byte array is totally different. But in HBase only recognizes byte array. There's no integer, floating, streaming, all those stuff. When we say x minus or less than something, if we do this way, less than 2, if we don't do any transform, just make 2 to the byte array, then less than this byte array, what do we get? We get this part only. We lost this part. Does it make sense? Because in the integer space, less than 2, that's okay. Go from this 2 all the way to the left. But in the byte array order, 0 is the minimum instead of the mean integer mean. 0 is the minimum byte array number. -1 is actually the maximum. So when we do the x less than equal to 2, we have to transform this into 2 range. One part is from 0 to 2. The other part is from the mean to the -1. This is that the other if x larger or equal to -2, if we don't do any transformation, we only get this part. We lose all of this part. That's how come we have some data loss in some implementation. So internally, this not only happen to the short integer, long also happen to the double and the float. Double and float is a little bit more complicated because the double and float, the negative part, actually the order is reversed. What I mean is in the integer and in the integer, although the negative is larger than the positive, but as long as the number is negative, the byte order still keeps the same. -2 less than -1. But actually in double or floating, that's different. -2.0 is actually larger than -1.0 in the byte array order. So we have to take care of that. And I will skip, but if you're interested, we can take it offline. But yeah, due to the time, I will skip this. So now how do we do the partition pruning or this performance improvement? On the one side, we have the query, we have the where clause, we transform all those conditions, maybe less than 2, transform to a multiple scan range on the one side. The other side, in the HBase, for each region, we have the starting point and the ending point for that specific region. So one side we have the scan range, the other side we have the start and the end for the region server. Then we do the intersect between these two range. Then we know exactly for this specific region server what scan range fall into that region server. Then we do this to all the region server. Then we know exactly which region server hold our data, which region server doesn't hold our data. Also, we know exactly which, for the region server that holding our data, what's the range, scan range for this region server. This is just a two set of range to do the intersect. We know all this information. Based on that, we constructed the RDD or the task to then send the task to only those region servers that having our data. Also have all the information in this region server, what scan range. Maybe there's multiple scan range for one region server. That's partition pruning. Data locality. Since we already know this region server having the data, we already know the scan need to be performed in this region server. Next thing is straightforward. From the HBase metadata, we know this region server's host. We just set the preferred location for this task. Then column pruning, that is, we get it from the Catalyst optimization engine. We construct all the required column to the scan and the bulk get. Then predicate push down is also straightforward, but we don't use any coprocessor. We just push those filters, for example, larger than or equal or string start with, some filter like this, put into the scan, then ship to the region server. The region server will do this for us. We don't need to worry about that. So scan and the bulk get. Group by region, what does it mean? Yeah, previously we already mentioned. We group all the scan and the bulk gets based on the group by the region server. So one task will send multiple scan and multiple gets to the region server. Okay. Yeah, then we decide we migrate, contribute all this code to the HBase upstream. Then HBase upstream, we already have the RDD implementation from Cloudera. Then if we add this one to the HBase upstream, then we have a complete solution for Spark. We both have the RDD, also have the data frame, so user can choose whatever fitting to their requirements. Currently, this is the JIRA number. 14789 is umbrella JIRA. I think most of them are already done. The other two critical part is this one, enhance a filter to handle those Java primitive type. This one not only handle those type, also have some critical bug fix. The bug fix, I think, is mainly there's some data loss is fixed in this one. The other is composite key support. This is like a new feature, but it's also fixed on some critical issue. I think is the data duplication got fixed in this bug. There's some also my colleague also work on some feature on this. Currently we are in this all got committed. These two. This one got reviewed, but still ongoing. The other one is I just submitted the patch for preview because this patch is built on top of this one. After all this is done, we will give a complete document how to use it. Okay, any question? Okay, thank you. If you don't have, okay. All right.
Between the executor, the Spark executor, and the region server, is it always a one-to-one communication? So can an executor talk to multiple region servers?
Ideally, we don't want to do that. In region server, if you the two region servers are not in the same host, for this executor, we only want this executor to talk to it locally.
For performance or for correctness?
No, not for correctness, for performance. But sometimes, if you don't have enough executor, you have more tasks than the number of executor or the number of calls. Then you have to, some tasks will waiting there for the first wave of the task get finished. Then you schedule the second wave of the task. Then here, if the preferred location that executor is not available, probably the scheduler will schedule the task to another executor. In that case, the executor will talk to the remote region server. So for data locality is the best effort. If you don't have enough computing resource, maybe you'll schedule your task to another executor.
And correctness is guaranteed by some rewriting?
Correctness is mainly handle those integer, floating, double, how to make it in the binary order and the Java primitive type order. The two orders are totally different. We have to take care of that. Otherwise, you definitely get some not correct result.
Thank you for your presentation. I have just one question concerning catalog definition. Is it possible in the future to use each catalog instead of defining the catalog in this form?
Yeah, for the H catalog, if you look at the Spark 2.0 code, actually now they kind of implement a lot of their own catalog implementation. But for this specific question, I think is the application level decision. If you want to use this connector, definitely you can have your own catalog, then you can persist all your HBase catalog, this catalog to your own catalog server, or you can write your catalog directly in your code. Yeah, either way. Whether you want to persist to the H catalog, probably we can take it offline. Yeah, I personally, I never think about that yet.
Because in our case, we started to use this connector, HBase data source for Spark, but we have more than 100 tables.
Oh, so maybe we talk offline. The time is running out. Yeah. Thank you.